The Rosetta mission to Comet 67P Churyumov-Gerasimenko, which orbited the comet from 2014 to 2016 and deployed the Philae lander, produced the most detailed chemical analysis of a cometary nucleus ever achieved. The Rosina instrument on board Rosetta detected 67P's outgassing material and found an inventory of organic molecules including ethanol, acetaldehyde, propanol, methyl isocyanate, and several others detected for the first time in cometary material. The isotopic ratios of hydrogen, oxygen, and nitrogen in the comet's water and nitrogen-bearing molecules were measured with high precision and compared to terrestrial values, providing constraints on the origin of Earth's water and nitrogen. The DH ratio, the ratio of deuterium to normal hydrogen in 67P's water, was found to be significantly higher than Earth's ocean water, suggesting that 67P-type comets from the Jupiter family were not the primary source of Earth's water, and pointing instead to asteroid-delivered water as more likely. The connections between cometary chemistry and molecular cloud chemistry, between the ices formed in dark cloud interiors and the ices delivered to forming planets, are being traced through comparative studies that use the molecular cloud inventory as the starting point and follow the chemical evolution through cometary and meteoritic material to the composition of primitive planetary bodies. ALMA, the Atacama Large Millimeter Array, an interferometric array of 66 radio telescopes in the Chilean Atacama Desert operating at millimeter and submillimeter wavelengths, has transformed the study of molecular clouds and star-forming regions in the decade since its completion in 2013. Its combination of sensitivity, resolution, and frequency coverage allows the mapping of molecular emission from cloud cores and protostellar disks at the resolution needed to study the chemistry and kinematics of the star formation process in detail that was previously inaccessible. ALMA observations have revealed the structures of protostellar accretion disks at tens of astronomical unit scales, mapped the emission of dozens of molecular species simultaneously in hot cores, and detected new interstellar molecules that have expanded the known inventory of interstellar chemistry significantly. The inventory is still growing. New molecules continue to be detected in interstellar clouds at a rate of several per year, and the full complexity of interstellar chemistry is still being revealed. Inside the dark molecular clouds, in the densest and coldest of their cores, something is happening that will eventually be visible as a new star. The process of star formation, the transformation of cold, diffuse gas and dust into a hot, radiating nuclear fusion reactor, is one of the most important processes in the galaxy. The mechanism by which the galaxy's gas and dust reservoir is continuously being converted into the stars that produce most of the light, heavy elements, and energy that characterize the galactic ecosystem. And it is happening right now, inside the dark patches that interrupt the Milky Way's glow. The beginning of the star formation process is the slow, gravitational contraction of a dense cloud core. A dense core is a region within a molecular cloud where the gas density has risen above a threshold, typically around 10 to the 4th to 10 to the 5th molecules per cubic centimeter, where the thermal pressure of the cold gas cannot indefinitely resist the inward pull of gravity. This threshold is given by the Jeans instability, named for the British physicist Sir James Jeans, who derived it in 1902. A self-gravitating cloud of gas will collapse if its mass exceeds the Jeans mass, which depends on the temperature and density of the gas. For the temperatures and densities typical of dense molecular cloud cores, the Jeans mass is of order 1 solar mass. which explains why the stars that form in molecular clouds tend to have masses in the range of fractions of a solar mass to several solar masses. The most common stellar types. The collapse of a dense core begins slowly and then accelerates. Initially, the contraction is isothermal. The core radiates away the energy produced by gravitational compression efficiently through molecular line emission and dust thermal emission, and the temperature remains roughly constant at 10 to 20 Kelvin. During this phase, the contraction time scale is the free fall time, approximately 10 to the 5th to 10 to the 6th years for a dense molecular core. As the density increases, the cloud becomes optically thick to its own thermal radiation, and the energy of gravitational compression can no longer escape freely. The temperature begins to rise, and the contraction slows to what is called a quasi-static contraction, slower than freefall, but still inexorable. This optically thick phase, when the central object has a luminosity generated by gravitational contraction rather than nuclear fusion, and a temperature too low to be called a star, is the protostellar phase. The protostar is surrounded by a disk of gas and dust, the protoplanetary disk, formed by the conservation of angular momentum as the rotating core contracted. Any small initial rotation of the core is amplified enormously as the core contracts, in the same way that a spinning figure skater accelerates by pulling their arms inward. The angular momentum must go somewhere, and it goes into a rotating disk perpendicular to the rotation axis. This disk is where the planets will eventually form, where the chemistry of the interstellar cloud will be concentrated and processed by the higher temperatures near the protostar, and where the dust grains that were drifting through the dark cloud will begin to stick together into the first generation of centimeter-sized pebbles that are the precursors of planetesimals and eventually planets. The protostellar disk is not featureless. ALMA observations of protostellar and protoplanetary disks have revealed a remarkable variety of ring, gap, spiral arm, and asymmetric structures in the dust distribution that are thought to be produced by forming planets, creating pressure bumps and gap-clearing zones in the disk. The most iconic of these images is the ALMA observation of the HL Tau disk, released in 2014, which showed a system of concentric bright and dark rings in the dust distribution of a disk around a protostar only about 1 million years old, far younger than had been expected to show planetary clearing signatures. The implication was that planet formation begins very early in the protostellar phase, within the first few million years of the disk's existence, rather than being a slow process requiring tens of millions of years. Subsequent ALMA observations of dozens of other young disks have confirmed that ring and gap structures are common in protostellar disks, and the challenge for planet formation theory is now to explain why this substructure is so ubiquitous and what it implies about the timing and mechanism of planet formation. The protostar phase ends when the temperature at the center of the contracting object reaches approximately 10 million Kelvin, the threshold for the ignition of hydrogen fusion. At this temperature, protons begin to fuse into helium through the proton-proton chain, releasing energy that counteracts the gravitational compression and establishing the hydrostatic equilibrium that defines a main sequence star. The object is now a star, radiating energy generated not by gravitational contraction, but by nuclear fusion, and it will remain in this state for the Sun for approximately 10 billion years until its hydrogen fuel is exhausted. The dark molecular cloud from which the star formed does not survive intact. The radiation at stellar winds from the new star heat and erode the surrounding material, dispersing the cloud and exposing the new stellar nursery to the interstellar medium. This process is called photodissociation region formation, and it is visible in the beautiful images of star-forming regions taken by telescopes including Hubble and the James Webb Space Telescope. The pillars of creation in the Eagle Nebula, the Carina Nebula's cosmic cliffs, the Orion Nebula's inner structure, all showing the illuminated boundaries between ionized gas and the remaining molecular cloud, the interface between the new stellar radiation and the dark material that has not yet been consumed. The JWST image of the pillars of creation, released in late 2022, showed structures embedded in the pillars that had been invisible in Hubble's optical images. Protostars still embedded in the pillar material, glowing in the infrared, each one a star in the process of being born, surrounded by a cloud of gas and dust that will eventually be dispersed by the star's own light and wind, releasing the new stellar object into the general stellar population of the galaxy. The Barnard Catalog of Dark Nebulae, compiled by the American astronomer Edward Emerson Barnard between 1905 and 1927 from photographic surveys of the Milky Way, established dark nebulae as genuine astronomical objects rather than gaps in the stellar distribution. Barnard photographed the dark patches systematically and cataloged 370 dark nebulae with their positions and estimated sizes, noting that many of the most prominent dark patches were associated with nearby bright nebulae and young stars, a connection that would eventually be understood as the relationship between molecular cloud complexes and the star formation they host. Some of the objects in the Barnard catalog, Barnard 68, Barnard 86, and others, have become iconic objects in the study of dark molecular clouds, photographed with modern instruments in extraordinary detail that reveal structure and complexity far beyond what Barnard could have appreciated with the photographic plates of the early 20th century. The Great Rift is the most prominent of the dark features in the Milky Way, visible to the naked eye as a dark lane that splits the Milky Way from the constellation Cygnus in the north to Centaurus in the south, dividing the bright band of the galaxy's disk into two irregular halves for much of its length. It is not a gap in the stars, but a dense chain of molecular clouds lying between roughly 300 and 1,000 light-years from Earth, absorbing the light of the stars behind them and creating the appearance of a dark region in the galaxy's glow. The Great Rift contains some of the best-studied molecular cloud complexes in the sky, including the Perseus, Taurus, Ophiuchus, Lupus, and Chamaeleon complexes, all of which are within a few hundred light-years of the Sun and are actively forming stars. The Taurus molecular cloud is one of the closest star-forming regions to Earth at approximately 430 light-years and has been studied in extraordinary detail as a prototype of low-mass star formation, the formation of stars like the Sun and lower, which form in relative isolation rather than in the dense clusters characteristic of massive star formation. The cloud extends over a region several degrees across in the sky and contains a population of roughly 200 young stellar objects, protostars, and very young T Tauri stars in the process of accreting material from their protoplanetary disks, spread over the cloud's area in a pattern that reflects the fragmented, filamentary structure of the cloud itself. Studies of the Taurus cloud with radio telescopes and infrared satellites have mapped the filamentary structure of the molecular gas in detail, finding that the densest filaments, the narrow thread-like structures where the gas density is highest, are the sites where the dense cores that will form stars are located, suggesting that filamentary structure plays a central role in channeling material toward the sites of star formation. Ophiuchus, sometimes called the Rho-Ophiuchi cloud complex, is another nearby star-forming region at approximately 400 to 450 light-years that has a different character from Taurus. While Taurus is dominated by isolated, distributed low-mass star formation, Ophiuchus contains a dense cluster of forming stars in its main core, the L1688 cloud, where more than 300 young stellar objects are embedded in a small volume only a few light-years across. This dense clustering reflects a different physical regime of star formation, where the high density of the cloud core allows multiple protostars to form in close proximity, potentially interacting gravitationally and producing a bound young cluster. The Ophiuchus cloud has been one of the targets of the ALMA Large Program D-Sharp, the disk structures at high angular resolution project, which image the protoplanetary disks of 20 young stars in nearby star-forming regions, including Ophiuchus, at a resolution of a few astronomical units, revealing the ring and gap structures in the dust distribution that are thought to be created by forming planets, clearing lanes in the disk. The Perseus molecular cloud, somewhat further at approximately 300 light-years, is notable for containing one of the most well-studied examples of a bipolar outflow, the NGC 1333 region, where a cluster of young protostars is driving powerful jets and outflows of gas into the surrounding cloud, creating a spectacular system of shocks and cavities visible in both molecular line emission and optical imaging. Bipolar outflows are a nearly universal feature of the protostellar phase, driven by magnetic fields and the accreting disk, and they play an important role in regulating the rate of star formation by injecting energy and momentum into the surrounding cloud and dispersing material away from the forming star. Without outflow feedback, star formation would proceed much faster than it does, rapidly converting the molecular cloud material into stars at a rate that would exhaust the galaxy's gas reservoir far more quickly than we observe. Beyond the nearby molecular cloud complexes of the Great Rift, deeper in the galaxy toward the galactic center, and in the spiral arms at distances of thousands of light-years, there exists a population of even denser, colder, more massive dark structures that are the sites of the most vigorous star formation in the Milky Way. These are the infrared dark clouds, structures that appear dark not just in visible light, but also in the mid-infrared, absorbing the diffuse infrared background emission of the galactic disk, and appearing as dark silhouettes against that background in infrared images. Infrared dark clouds were discovered in the late 1990s in data from the Mid-Course Space Experiment satellite, and have since been cataloged in thousands across the galactic plane by the Spitzer Space Telescope's Glimpse survey. An infrared dark cloud can contain masses of gas and dust ranging from a few hundred to several 100,000 solar masses, often distributed in complex filamentary morphologies that reflect the combined influence of gravity, turbulence, and magnetic fields on the cloud structure. The densest regions within infrared dark clouds, infrared dark cloud cores, have densities exceeding 10 to the 6 molecules per cubic centimeter and temperatures as low as 8 to 10 Kelvin, making them among the coldest and densest environments in the interstellar medium. These extreme conditions make infrared dark cloud cores the sites of the next generation of massive stars, O and B-type stars many times more massive than the Sun, which burn their fuel faster, live shorter lives, and play a disproportionate role in the energy budget and chemical enrichment of the galaxy. massive stars form in a qualitatively different way from the sun-like stars forming in the Taurus and Ophiuchus clouds. The formation of a star, much more massive than the Sun, faces a specific physical challenge: radiation pressure. As a forming massive star accumulates mass from the surrounding cloud, its luminosity increases rapidly with mass, and the radiation pressure on the infalling dust can, above a certain accretion rate, reverse the infall and halt the accretion. How massive stars overcome this radiation pressure barrier has been one of the central problems in star formation theory, and the resolution appears to involve the accretion of material through a disk and in the form of unstable filamentary streams that can penetrate the radiation pressure barrier, channeling mass onto the forming star from directions where the radiation pressure is lower, while allowing radiation to escape in other directions. ALMA observations of massive protostars have revealed the disk structures and filamentary accretion streams predicted by these models, with sufficient detail to begin testing the theory quantitatively. The consequences of massive star formation for the surrounding molecular cloud are dramatic. A massive star born in the interior of a molecular cloud quickly begins ionizing the surrounding gas with its intense ultraviolet radiation, creating an HII region, a bubble of ionized hydrogen surrounding the star. This HII region expands into the surrounding molecular cloud, heating it and eventually dispersing it. The expansion of the HII region compresses the cloud material at its boundary, potentially triggering new episodes of star formation at the edge of the region, a process called triggered star formation that has been observed in several well-studied examples of HII regions embedded in molecular clouds. The massive star also drives a powerful stellar wind, and eventually, after only a few million years, explodes as a supernova, producing a shock wave that propagates through the surrounding gas and dust, further dispersing the cloud and potentially triggering yet another episode of star formation in the compressed shell behind the shock. This cycle, molecular cloud-forming stars, massive stars ionizing and dispersing the cloud, supernova shockwave triggering star formation in the next cloud, is called the supernova triggering or collect and collapse model of star formation, and is thought to be one of the mechanisms by which star formation propagates across a galaxy's spiral arms. The dark molecular clouds that appear to be passive, quiet objects against the bright background of the Milky Way are, in this picture, dynamic participants in an ongoing cycle of gas cycling between diffuse and dense phases, of energy input from stellar feedback, of chemical enrichment from stellar nucleosynthesis, that has been operating for the entire history of the galaxy and continues tonight in the dark lane of the Milky Way, visible from a dark sky location. The darkest region of the Milky Way from an optical observation perspective is the galactic center itself, the region towards Sagittarius, where the density of dust in the galactic plane is so high that virtually no optical light from the galactic center reaches us. The stars and gas and molecular clouds of the galactic center, which lie 26,000 light-years away, are hidden behind roughly 25 magnitudes of visual extinction, an attenuation factor of 10 to the 10th, meaning that a star at the galactic center 1 billion times brighter than a star visible to the naked eye would be invisible optically. The galactic center has been studied for the past several decades almost entirely in infrared, radio, and X-ray wavelengths, which penetrate the foreground dust. What has been revealed in those other wavelengths is one of the most complex and extreme environments in the galaxy. The central 100 light-years of the Milky Way contain a concentration of molecular gas far denser than anywhere in the disk, the central molecular zone, a region containing several tens of millions of solar masses of molecular gas, in a volume of roughly 150 by 50 light-years, with average gas densities thousands of times higher than in the molecular clouds of the galactic disk. The central molecular zone contains some of the most massive molecular clouds in the galaxy. Sagittarius B2, the most massive molecular cloud in the Milky Way, is a complex of clouds with a total mass of several million solar masses and a central density high enough to make it the site of one of the richest interstellar chemical inventories in the galaxy. Sagittarius B2 has been a particularly productive site for the detection of new interstellar molecules. The physical reason for the molecular richness of SGR B2 is a combination of its high density and column density of material, which provides excellent shielding from the photodissociating UV radiation of the galactic center, and the presence within it of hot cores, compact, warm, dense regions surrounding newly formed massive protostars, where the elevated temperatures, 100 to 300 Kelvin, compared to 10 to 30 Kelvin in the cold outer cloud, cause the ice mantles on dust grains to sublimate, releasing their accumulated molecular inventory into the gas phase. In hot cores, the chemistry is driven not by cold surface reactions, but by gas phase reactions at elevated temperatures, and the competition between these different chemical regimes produces a molecular inventory of extraordinary richness. The hot cores within SGRB2, designated SGRB2N and SGRB2M, have each been the site of numerous molecular detections, and the survey of these regions with high-resolution, high-sensitivity radiospectroscopy remains one of the most productive activities in astrochemistry. Sagittarius B2 has been a particularly productive site for the detection of new interstellar molecules, including the first detections of several dozen molecular species, among them ethanol, acetaldehyde, propan-2-ol, and most recently, propargocyanide, each detection extending the known complexity of interstellar chemistry and constraining models of the chemical pathways operating in hot core environments. The central molecular zone is threaded by a system of unusual, non-thermal radiofilaments, long, thin structures extending perpendicular to the galactic plane, visible in radio continuum images as bright threads against the background. These filaments, first discovered by radio astronomer Farhad Yousafzadeh in 1984, are believed to be magnetically ordered structures illuminated by relativistic electrons spiraling along the galactic magnetic field lines, which near the galactic center are oriented perpendicular to the plane, in contrast to the field lines in the galactic disk, which run roughly along the plane. The origin of the relativistic electrons illuminating the filaments is thought to be related to the activity of the central region, the infall of material onto Sagittarius A star, or the remnants of past star formation episodes in the central parsecs, though the specific mechanism and the connection between the filaments and the central engine remain topics of active research. At the very center, within a few light-years of Sagittarius A star, the environment becomes extreme by any measure. The tidal forces from the black hole are strong enough to prevent dense molecular clouds from surviving close to the center. But diffuse gas and dust still orbit and in some cases fall onto the central black hole. In 2013 and 2014, astronomers watched with unusual excitement as a cloud of gas and dust, designated G2, approached within a few hundred astronomical units of Sagittarius A star on a very close orbit. The encounter did not produce the spectacular flaring that some predicted. The cloud was disrupted and stretched by the tidal forces, but did not produce a prolonged accretion event. But it demonstrated the ability of modern infrared instruments to monitor the infall of material near the galactic center in real time, and provided a case study in the interaction between the diffuse interstellar medium and an active supermassive black hole. High above and below the galactic plane, far from the dark molecular clouds of the disk, extends a pair of gigantic structures that were discovered in 2010 in data from NASA's Fermi Gamma Ray Space Telescope, and that have fundamentally changed our understanding of the recent history of the galactic center. The Fermi bubbles are two roughly spherical lobes of gamma-ray emitting material, each approximately 25,000 light-years tall, extending symmetrically above and below the galactic center like two giant balloons inflated from the galactic plane. Together, they span approximately 50,000 light-years, roughly half the diameter of the Milky Way's disk, and they contain a total energy of approximately 10 to the 55th ergs, or roughly 10 million supernova explosions worth of energy. The Fermi bubbles are not molecular clouds or dark regions. They are hot, diffuse, gamma-ray emitting structures whose sharp edges are visible against the diffuse gamma-ray background of the galaxy. But their existence is intimately connected to what has been happening in the dark molecular clouds of the galactic center, because the energy that inflated them came from the galactic center, either from a past period of much greater activity of Sagittarius A star, or from an intense episode of star formation in the central parsecs, or both. The two hypotheses for the Fermi bubble's origin, a past AGN jet from Sagittarius A star, and a nuclear starburst wind, make somewhat different predictions about the detailed structure and composition of the bubbles, and are being tested with current and future observations. The sharp edges of the Fermi bubbles, visible in both gamma rays and in X-ray emission from the hot gas at the boundaries, suggest that the energy injection event was relatively recent in cosmic terms, within the last few million years, because the sharp boundaries would diffuse and soften if the structures were older. This relatively recent energy injection, coming at a time when the early hominids were already present on Earth, connects the story of the galaxy's most energetic recent event to the story of human evolution on a planet orbiting a star in the quiet outer disk, 26,000 light-years from whatever was happening at the galactic centers several million years ago. The bubbles had no effect on the solar neighborhood at their formation, but their existence tells us that the galactic center was far more energetically active in the geologically recent past than it is today, and that the apparent calm of Sagittarius A star in the present is not its permanent state, but a current lull in an episodically active central engine. Zeta, the X-ray telescope launched in 2019 on the Russian-German Spectrum Röntgen Gamma mission, detected an even larger structure associated with the Fermi bubbles. The Rosetta bubbles, which extend to approximately 40,000 light-years above and below the galactic plane, and correspond to the forward shock driven by the expansion of the Fermi bubble region into the surrounding hot gas of the galactic halo. The Rosetta bubbles, announced in 2020, are the X-ray counterpart of the Fermi bubbles, and together they paint a picture of the galactic center as a former Seyfert galaxy, a galaxy with a moderately active nucleus, whose activity has since declined to the quiescent state of Sagittarius A star we observe today. The dark regions of the galactic center, the molecular clouds that are hidden behind the obscuring dust of the disk, were the fuel for that past activity, and the remnants of that activity are now visible in the giant structures above and below the galactic plane. One of the most important and least visible of the physical agents structuring the dark molecular clouds is the interstellar magnetic field. The magnetic field of the Milky Way permeates the entire interstellar medium, including the molecular clouds, and it plays a crucial role in controlling the rate of star formation, the structure of the clouds, and the transport of energy and momentum through the cloud material. Yet the magnetic field leaves no direct imprint on the optical appearance of the dark clouds. It is invisible in the sense that you cannot point a camera at it and see it. Its presence is detected through indirect effects. The polarization of starlight as it passes through clouds containing dust grains partially aligned by the magnetic field. The polarized emission of the dust grains themselves at sub-millimeter wavelengths. The Zeeman splitting of molecular spectral lines in regions where the field is strong enough to lift the energy degeneracy of magnetic quantum states. The role of the magnetic field in star formation is one of the central debates in the field. In the magnetically regulated star formation picture, the interstellar magnetic field provides sufficient support against gravitational collapse that star formation can only proceed as the field slowly diffuses through the neutral gas, a process called ambipolar diffusion, in which the weakly ionized neutral gas gradually separates from the magnetic field while the field remains coupled to the ions and electrons. The ambipolar diffusion timescale is typically much longer than the freefall time, which would explain why star formation is so slow compared to what would be expected if gravity were the only relevant force. In the turbulence-dominated picture, by contrast, the magnetic field is less important than turbulent kinetic energy in supporting clouds against gravity, and star formation is regulated primarily by the dissipation of turbulence on small scales. The observational evidence suggests a picture intermediate between these two extremes. Magnetic fields are important in the outer, lower density regions of molecular clouds, where the field is relatively strong compared to gravity, while turbulence dominates in the denser core regions, where the magnetic field is less able to support the gas against the stronger gravity. The detailed quantitative characterization of magnetic field strengths in molecular clouds requires observations that are technically very challenging. The Zeeman effect measurements needed to determine field strengths in dense cold gas require extraordinarily sensitive radio receivers and long integrations on single targets, and the current sample of measured field strengths is limited compared to what is needed for a comprehensive statistical characterization of the magnetic field role in star formation. The Planck satellite, which operated from 2009 to 2013 and mapped the cosmic microwave background in unprecedented detail, also produced all-sky maps of the polarized dust emission from the Milky Way at sub-millimeter wavelengths, providing the most comprehensive picture of the magnetic field structure of the interstellar medium ever assembled. The Planck polarization maps reveal a magnetic field that follows the large-scale structure of the galaxy, running along the spiral arms and the disk, but with significant small-scale structure in the molecular clouds, where local conditions, including the turbulence and the influence of nearby stellar feedback, have distorted the field from its large-scale orientation. The structures visible in the Planck polarization maps, the complex, ordered patterns of dust grain alignment that trace the field geometry, are a glimpse into the invisible architecture that is shaping the dark clouds of the Milky Way and determining where and when star formation will occur within them. One of the most striking results from Planck's polarization study of molecular clouds is the finding that the elongated filamentary structures in molecular clouds, the dense threads of gas and dust that run through the cloud and along which dense cores form, tend to be oriented perpendicular to the local magnetic field direction. This anti-correlation between filament orientation and field direction is the opposite of what might be naively expected if the magnetic field were simply compressed along with the gas during cloud formation. It suggests instead that the filaments form by gas flowing along the magnetic field lines and accumulating in regions where the field geometry focuses the flow, rather than by compression across the field. The filaments are, in this picture, the natural consequences of magnetized turbulence, the channels along which gas flows from the diffuse interstellar medium into the dense regions where star formation occurs, guided by the invisible magnetic architecture of the interstellar medium. The dark clouds of the Milky Way are not random aggregations of gas and dust. They are the visible expression of a structured, magnetic, turbulent medium that has been organizing the material of the galaxy for billions of years. The dark molecular clouds of the Milky Way are not permanent structures. They are transient configurations of gas and dust, maintained temporarily by the balance of gravity, turbulence, and magnetic field pressure against the stellar feedback that would otherwise rapidly disrupt them, and they will eventually be converted into stars or dispersed back into the diffuse interstellar medium. The lifetime of a molecular cloud is typically estimated at 10 to 30 million years. In galactic terms, a relatively short time, comparable to the orbital period of the solar system around the galactic center. In that time, the cloud will convert some fraction of its gas into stars, with the fraction, the star formation efficiency, typically a few percent per free fall time, meaning that only a small proportion of the cloud's mass ends up in stars before the feedback from those stars disperses the remaining gas. The stars formed in the dark clouds do not stay in the dark. As the molecular cloud disperses under the influence of stellar feedback, the young stars that formed within it are released into the general disk population, gradually dispersing away from their birth site over hundreds of millions of years as the perturbations of other stars and the galactic gravitational potential scatter them. The atoms that were frozen onto dust grains in the cold cloud interior, the complex molecules assembled through grain surface chemistry and gas phase reactions over millions of years in the dark, all of this is eventually incorporated into the forming stars and their planetary systems, or dispersed back into the interstellar medium where it becomes the raw material for the next generation of clouds. The carbon in your body was forged in the nuclear burning of a star that lived and died before the sun formed. The water in your cells was assembled in a molecular cloud and incorporated into the solar nebula during the formation of the solar system. The dark clouds are the place where this transformation happens, the place where diffuse interstellar material is concentrated, chemically enriched, and eventually converted into the stars and planets and molecules that comprise the galaxy's complex ecosystem. The specific dark clouds visible in the Milky Way tonight, the Taurus cloud, the Ophiuchus cloud, the Perseus cloud, the clouds of the Great Rift, the infrared dark clouds of the inner galaxy, are in various stages of this process. Some are in the early stages, quiescent and cold, with no stars yet forming within them. Some are actively forming stars, with protostars embedded in their dense cores and bipolar outflows carving cavities in the surrounding material. Some are in the dispersal stage, their cloud structure disrupted by stellar feedback, and the remaining gas rapidly dispersing into the surrounding interstellar medium, while the young stars they formed drift away from their birth sites. In a few tens of millions of years, most of these specific clouds will be gone, converted into stars or dispersed, and new molecular clouds will be assembling from the diffuse gas of the interstellar medium, condensing along the spiral arms, and in the cold compressed gas behind the passage of the galactic magnetic field, ready to begin the process again. The specific star formation rate of the Milky Way, the mass of new stars formed per year, has been measured from surveys of young stellar objects, HII regions, and massive star tracers across the galactic disk, and is approximately 1 to 3 solar masses per year. This seems modest, but compounded over the galaxy's lifetime of roughly 10 billion years, it accounts for the observed stellar mass of the galaxy. The star formation rate has not been constant. It was higher in the early galaxy, when gas was more abundant, and when the first generations of massive stars were enriching the interstellar medium with heavy elements that facilitate cooling and fragmentation. But it has been relatively steady in the current epoch, sustained by the continuous return of gas from evolved stars and the accretion of pristine gas from the galactic halo. The dark molecular clouds that form tonight will form stars that return some of their mass to the interstellar medium billions of years from now, sustaining the next generation of molecular clouds and the stars that will form within them. The galaxy is not running out of gas. The interstellar medium that feeds the molecular clouds is continuously replenished by the return of gas from evolved stars, through stellar winds from old red giants, through the planetary nebulae cast off by dying sun-like stars, through the supernova ejecta of massive stars that return most of their mass to the interstellar medium. This return of gas, enriched with the heavy elements produced by stellar nucleosynthesis, gradually increases the metallicity of the interstellar medium and the stars that form from it, enriching each successive generation of stars with a higher proportion of carbon, oxygen, nitrogen, iron, and the other elements that make complex chemistry and planetary systems possible. The dark clouds of the Milky Way are part of a galaxy-wide cycle of gas recycling, stellar birth and death, and chemical enrichment that has been running for 10 billion years and will continue for billions more. Tonight, in the dark regions of the Milky Way, 10 to 30 Kelvin above absolute zero, in clouds too cold and dense and distant for any current telescope to resolve their smallest structures, new stars are forming. Not one or two, hundreds, thousands, distributed across the molecular cloud complexes of the disk, each one a protostar, accumulating mass from a collapsing core that was, 100,000 years ago, indistinguishable from the quiescent cold gas around it. Each forming star is surrounded by a disk where the first generation of its planets is beginning to assemble from the dust and ice of the cold molecular cloud, carrying with it the molecular inventory of the cloud from which it formed, the amino acid precursors, the simple sugars, the complex organics that grain surface chemistry assembled over millions of years in the dark. The dark is alive with the work of gravity and chemistry and magnetic fields. The dark lanes of the Milky Way are not gaps in the galaxy's story. They are the places where the next chapter is being written, in cold and silence and slow molecular time, waiting for the light that will eventually emerge from within them. The Square Kilometer Array, the SKA, currently under construction in South Africa and Australia, and expected to see first light in the late 2020s, will transform the radio study of the interstellar medium in ways that complement the ALMA observations at millimeter wavelengths. The SKA will survey molecular clouds in previously inaccessible spectral lines, map the distribution of atomic hydrogen across the galaxy with unprecedented sensitivity and angular resolution, Monitor the magnetic field structure through pulsar rotation measures across the galaxy, and search for new complex molecules in the interstellar medium at centimeter wavelengths, where many of the most complex organic molecules have their rotational transitions. Combined with the ongoing capabilities of ALMA and the planned future space infrared missions, the next decade will see a transformation in our understanding of the chemical inventory of the dark regions of the Milky Way and the processes by which that inventory is assembled and delivered to forming planetary systems. The dark regions of the galaxy are, in this context, among the most active scientific frontiers of the coming decade, places where the questions of the origin of life's chemical building blocks, the rate and regulation of star formation, and the structure of the galactic magnetic field all intersect in ways that require observations at every accessible wavelength to disentangle. You are here, on a planet formed from the material of a dark molecular cloud 4.5 billion years ago, breathing the oxygen made by generations of stars, drinking water whose hydrogen was made in the Big Bang and whose oxygen was forged in stellar fusion, living in a body assembled from atoms that have been through every phase of the galactic gas cycle. You are made of what comes out of the dark clouds when they are done with their slow work. The Herschel Space Observatory, which operated from 2009 to 2013 and surveyed the far infrared sky with sensitivity far exceeding any previous mission, produced the High-Gal survey, the Herschel Infrared Galactic Plane Survey, which mapped the entire Milky Way disk at 5 wavelengths from 70 to 500 microns, and revealed the thermal emission of cold dust in molecular clouds and protostellar cores across the galaxy in unprecedented detail. The High-Gal survey has been the primary data source for catalogs of cold dust clumps and dense cores throughout the galactic plane, providing samples of hundreds of thousands of star-forming structures at various evolutionary stages that are being analyzed to understand the statistical properties of star formation across the diversity of galactic environments, from the nearby molecular clouds of the solar neighborhood to the crowded high-pressure environments of the inner galactic disk and the central molecular zone. The High-Gal survey has provided the first complete census of cold star-forming material in the Milky Way, establishing the baseline from which the next generation of infrared and radio telescopes will build. Rest now. The dark is working, as it always has, with a patience that makes all urgency look temporary. The molecular clouds are quietly, coldly, steadily becoming the next generation of stars. The galaxy is doing what it has done for 10 billion years, and will do for 10 billion more. And the dark regions of the Milky Way, from where you are lying, are invisible and extraordinary and entirely real, doing their work in the cold and the silence, whether you look up or not. Look up on a clear, moonless night, far from any city, and let your eyes adjust for 20 minutes. What appears first is the obvious: the stars, scattered across the sky in their thousands, bright and dim and steady. But as the dark adaptation deepens and the rods of your retinas become fully sensitive, something else becomes visible: a soft, irregular band of light, stretching from horizon to horizon, wider in some places and narrow in others, brighter toward the south in summer, and forming a great arc across the winter sky. This is the Milky Way, the galaxy we live in, seen from inside. And its light is not the light of a single thing, but the accumulated glow of hundreds of billions of stars, too distant to resolve individually, blurring together into the river of light that every human culture has noticed and named and woven into mythology since before the first writing. Threaded through that band of light, interrupting it in places, broadening into dark patches in others, are regions where the light stops. Not where the stars thin out or where clouds block the view, but where something dense and dark lies between the stars and your eyes, something that absorbs the light of the stars behind it and leaves a gap in the Milky Way's glow that is not emptiness, but presence. These dark regions have their own names, their own characters, their own stories. The Great Rift, which splits the Milky Way for much of its length in the summer sky. The Coal Sack, a dark patch near the Southern Cross. The Horsehead Nebula, the Pipe Nebula, the Barnard 68 cloud, a nearly perfect sphere of darkness against the star background of Ophiuchus. These dark regions are where the galaxy hides its most active work. They are the nurseries of new stars, the warehouses of molecular complexity, the sites where the chemistry of life is being assembled in the cold and dark by physics that needs no biology to proceed. They are cold, temperatures of 10 to 30 Kelvin, barely above absolute zero. They are dense, thick enough to block the light of millions of background stars with only a few light-years of material. And they are alive with chemistry. Hundreds of molecular species have been detected in the dark clouds of the Milky Way, including amino acids, sugars, and the precursor molecules of DNA. Tonight we will travel into the dark. Not the darkness of space between the galaxies, which is the emptiness of expansion, but the darkness of the Milky Way's own cold clouds, the molecular clouds, the dark nebulae, the infrared dark clouds, the dense cores where gravity is quietly doing its work. We will find that the dark regions of the Milky Way are not absences. They are the most productive places in the galaxy. The places where stars are being born tonight, where planets are forming, where the chemistry of life has been in preparation for billions of years. The room is dark and quiet. The night is patient. And in the dark lanes of the Milky Way, something extraordinary is happening. The first thing to understand about the dark regions of the Milky Way is what they are made of, because the darkness itself is a physical substance with a specific composition and structure that has been characterized in considerable detail. The dark patches in the Milky Way are made primarily of interstellar dust, tiny solid particles, typically between 1/10 of a micron and a few microns in diameter, composed of silicate minerals and carbonaceous material, often with icy mantles of water, ammonia, methanol, and other frozen molecules coating their surfaces. These dust particles are the residue of stellar evolution, material ejected from the outer atmospheres of evolved stars, from the winds of cool giants, from the ejecta of supernova explosions, drifting outward into the interstellar medium, and gradually accumulating into the clouds we observe as dark patches against the stellar background. A single dust particle in the interstellar medium may have traveled for millions of years since being exhaled by a dying star, may have traveled through several different interstellar cloud environments, and may have been partially processed by the radiation it encountered on its journey before settling into the relatively protected interior of a dense molecular cloud. The dust is opaque to visible light because the particle sizes are comparable to the wavelengths of visible light, allowing efficient scattering and absorption. A region of interstellar space with enough dust to appear dark to the naked eye has an optical depth, a measure of how many photon path lengths of absorbing material it contains, of at least 1, meaning that a typical photon of visible light passing through it has a probability of more than 60% of being absorbed or scattered before it gets through. The densest dark clouds, like Barnard 68, have optical depths of more than 35 in the visual band, meaning that visual light is attenuated by a factor of e to the power 35, or approximately 10 to the power 15. A source 100 million times brighter than the brightest star in our sky, placed directly behind Barnard 68, would be invisible in optical light. The cloud is not merely dim to visual observation. It is opaque in a way that essentially no starlight penetrates. But the dust that blocks visible light is transparent to longer wavelengths of radiation. The same cloud that is completely opaque to optical light can be studied in exquisite detail in the infrared, and with radio telescopes, the molecular gas within the cloud can be mapped through the rotational emission lines of molecules at millimeter wavelengths. This wavelength dependence of the dust opacity is what has allowed astronomers to peer inside the dark clouds and map their structure, their temperature, their density, and their chemical composition with a precision that would have been impossible before radio and infrared astronomy became mature observational tools in the second half of the 20th century. The dust is also not alone. The dark molecular clouds contain gas, primarily molecular hydrogen, which is the most abundant molecule in the universe, and which cannot be directly observed in cold molecular clouds because it produces no emission at the temperatures typical of cloud interiors. The presence of molecular hydrogen is inferred from the emission of other molecules. Carbon monoxide, which is the second most abundant molecule and which has a strong rotational emission line at millimeter wavelengths, and from the many other molecular species whose emission traces the conditions within the cloud. The ratio of gas to dust in the interstellar medium is approximately 100 to 1 by mass. For every gram of dust, there is approximately 100 grams of gas. The clouds appear dark because of the dust, but their mass is dominated by the gas. The temperatures inside the densest molecular cloud cores are astonishingly cold. Typical temperatures in the outer parts of a molecular cloud are 20 to 30 Kelvin, about minus 250 degrees Celsius, only 20 to 30 degrees above absolute zero. In the densest core regions, where the cloud is opaque enough to shield itself from all external radiation, temperatures can drop to as low as 8 to 10 Kelvin. At these temperatures, the thermal energy of the molecules is so low that almost all chemical activity has ceased in a classical sense. The molecules do not have enough thermal energy to overcome the activation barriers of ordinary chemical reactions. The chemistry that does occur in these cold, dense cores operates by different mechanisms, by quantum mechanical tunneling of light atoms through reaction barriers, by reactions on the surfaces of dust grain ice mantles where molecules can accumulate and react more readily than in the gas phase, and by the ionizing radiation of cosmic rays that penetrates even the densest cloud interiors and provides a trickle of chemical energy that drives a slow but diverse chemistry, even at these extreme temperatures. The cosmic rays that penetrate the dark molecular clouds deserve special mention. because they are the primary energy source for the chemistry and ionization of the cloud interior in the absence of starlight. Cosmic rays are high-energy particles, predominantly protons and heavier atomic nuclei, that permeate the entire galaxy and are produced primarily by supernova remnants, where particles are accelerated to relativistic velocities by the expanding shock waves. Because cosmic rays are charged particles, they are deflected by the galactic magnetic field and travel along curved paths rather than straight lines, making it difficult to trace any individual cosmic ray back to its source. But their collective flux throughout the galaxy is well characterized from observations, and their effect on molecular cloud chemistry is significant. A cosmic ray proton passing through a molecular cloud ionizes the hydrogen molecules it encounters, producing H2+ ions that rapidly react with the surrounding neutral hydrogen to produce H3+, one of the most important ions in interstellar chemistry. H3+ reacts readily with other species, initiating reaction chains that eventually produce the complex molecular inventory of the dark cloud. In this sense, the violent supernova remnants that accelerate cosmic rays are indirectly connected to the gentle, complex chemistry of the cold molecular clouds. The same stellar explosions that return heavy elements to the interstellar medium also provide the ionizing radiation that drives the chemistry that builds the precursors of life in the next generation of molecular clouds. One of the most remarkable things about the dark molecular clouds of the Milky Way is the chemical complexity they contain. More than 270 distinct molecular species have been detected in the interstellar medium, a majority of them in the dark molecular clouds where the conditions are most favorable for molecule formation and survival. These molecules range from simple diatomics, carbon monoxide, hydrogen cyanide, sulfur monoxide, to complex organic molecules with dozens of atoms: methyl formate, dimethyl ether, glycoaldehyde, ethanol, acetaldehyde. In the hot cores associated with forming protostars, where the temperatures are elevated and the ice mantles on the dust grains evaporate, even more complex molecules have been detected, including amino acid precursors and simple sugars. The detection of these complex molecules in space was not initially expected. The standard picture of the interstellar medium as a radiation-bathed, collision-poor environment suggested that complex molecules would be rapidly photodissociated by ultraviolet radiation and would not accumulate to detectable levels. But the dark clouds provide exactly the shielding from UV radiation that allows molecules to accumulate. The outer layers of the cloud absorb and scatter the UV, protecting the interior where the molecular inventory can build up over the cloud lifetime of millions of years. The chemistry in the cloud interior is slow by laboratory standards, but slow chemistry over millions of years in a large cloud can produce significant quantities of complex molecules. The surface chemistry on dust grains is particularly important in the synthesis of complex molecules. When atoms and simple molecules freeze out onto the icy surfaces of dust grains, which are coated with mantles of water ice, CO ice, CO2 ice, and other frozen volatiles at the low temperatures of the cloud interior, they find each other in a two-dimensional surface environment that dramatically increases reaction rates compared to three-dimensional gas phase chemistry. A hydrogen atom adsorbed onto a grain surface can migrate rapidly across the surface by quantum tunneling, encountering other adsorbed species and reacting with them to form more complex molecules. The ice mantle grows over time, incorporating the products of these surface reactions, and eventually reaches a composition that contains not just simple ices, but complex organic molecules built up layer by layer through the cumulative effects of surface chemistry over millions of years. The glycine question is one of the most actively discussed in astrochemistry. Glycine is the simplest amino acid, one of the 20 amino acids used in the proteins of all terrestrial life, and it is the amino acid most expected to be detectable in the interstellar medium based on its chemical simplicity. It has been tentatively detected in meteorites. The Murchison meteorite contains glycine, and there have been searches for it in hot cores and dark clouds by radio telescopes, including the IRAM 30-meter telescope and the Atacama Large Millimeter Array. The searches have not yet produced a confirmed detection, but the upper limits established by the searches constrain models of interstellar glycine chemistry and the detection in cometary material. Glycine was detected in the coma of Comet Wild 2 by the Stardust mission and in Comet 67P by the Rosetta spacecraft, suggests that the molecule can form in icy environments similar to those on interstellar dust grains and be delivered to forming planetary systems with the comet-forming material.